Hey everyone, it's Colin. How's it going? We've seen some major technological advancements in just the last 20 years, especially when it comes to computers. You can probably think of at least a few things that have had a major impact on your life. But there's one that's not very visible, yet helps power the internet as we know it. This time, let's talk about virtualization. So virtualization is definitely not a new concept, at least given the accelerated nature of computer advancement, but it really began to be adopted in earnest in kind of the mid to late 2000s. It's definitely been around longer than that, though. Simply enough, virtualization is kind of the concept of running a computer within another computer. You can have multiple operating systems that are unrelated to each other share a computer's hardware resources. And it really all started with the idea of efficiency. It allows you to take advantage of hardware resources that are otherwise underutilized. Think about your computer. Maybe if you're sitting in front of a desktop or a laptop right now, in Windows, open up Task Manager and see what is showing up on that performance tab. What's your average CPU sitting at? How much RAM are you actively using versus what's free? And then how much hard drive space do you have that's free? Chances are most of the time that your computer is turned on, it's not using much CPU, it's not using much RAM, and you've got a decent amount of free hard drive space. Now, when it comes to things like servers, that's a bit of a waste of resources because most applications that servers run are very similar to the way that you interact with your own computer, where they're kind of bursty. They periodically get requests to process information where they'll get busy, they'll ramp up the load on the CPU, they'll consume some more RAM, and then after a while, that load will come back down and the system will be idle. So when servers are idle, that's really a waste of resources, which turns into a waste of money. So the point behind virtualization is to take advantage of that and put all of those idle resources to good use. Now let's take a step deeper and actually talk about really the nuts and bolts of virtualization. I should note there's a big difference between virtualization and emulation. Sometimes they get used interchangeably, but that is not correct. With virtualization, it's when you have similar processor architectures. So you can have a virtualized system pass, say, its CPU requests directly down to the hardware to be executed without having to really translate or change those requests. It's the idea of, let's say you've got a x86 based virtual machine running, say, Windows or Linux, and you're running it on top of hardware that's based on x86 that has an AMD or Intel CPU in it. You don't need to change any of the instruction sets or anything like that going from one to the other. The hardware is natively capable of running whatever the virtual machine is requesting of it. The difference is emulation is for dissimilar processor architectures. So you think of, say, firing up a Sega Genesis emulator on a Windows PC. Now, the Sega Genesis hardware, that original hardware, was based on a Motorola 68000 processor, but your Windows PC is probably based on an x86 processor. The two have very different instruction sets. You can't take code that was designed to be run on a Motorola 68000 and hand that to an Intel or AMD CPU and expect it to just be able to run it. It doesn't know what you want it to do. It's like it's speaking a different language. So what an emulator does is it acts as an interpreter or a translator. It knows how to speak both 68000 code and x86 code and can translate between the two. And that's how an emulator works. So you can fire up like that Sega Genesis game, and the emulator software that you're running knows, okay, when the game requests the hardware to do this function, I rewrite the function in this way, and then I can pass it on down to the CPU to be executed. And likewise, when the results come back, it knows how to translate that back into a result that the game software expects to see. The problem with emulation is that it's often not very efficient. Sometimes it's terribly inefficient because of how different processor architectures can be. So if you look at like game emulators, some of them can run on very low power hardware, but some game emulators require very powerful PC hardware to run consoles that are decades old. That's just how inefficient the emulator is. The beauty to virtualization is there's very, very little performance loss by running a machine in a virtualized environment, simply because you don't have to do any of that translation. It's kind of like everything is all speaking the same language. Now, you can have things in very different layers within the virtualization stack. There's really kind of 3 layers to them when you're looking at virtualization as kind of a core technology. The first one, of course, is hardware. Like, what type of hardware are you running it on, whether it's a desktop or a laptop or a server, and then the processor architecture that it's running on. In the vast majority of cases, virtualization is running on x86 hardware because that's the most common kind of software that needs to get run in virtualization, right? Just commodity operating systems. The next layer in is arguably the most interesting one, and it's called the hypervisor or host layer. The hypervisor could be as simple as an application running on top of a full operating system. So if you've ever run something like VirtualBox or VMware Player on top of, say, Windows or Mac OS or Linux, then that's a very simple type of hypervisor type of setup. Or the hypervisor could be more dedicated to its function and actually be kind of rolled into an operating system itself. It could be a very small, lightweight operating system that is built exclusively to be a hypervisor. It's not really good at doing anything else, but you load that on top of the hardware, and then it handles all of the functions of managing the virtual machines. Now, the hypervisor does both that management function in terms of allowing you to power virtual machines on and off, or getting access to the console of being able to like use the keyboard and mouse and see what's on kind of the virtual screen of the VM. But it also does a lot of lower level functions too, like managing memory, because obviously virtual machines are going to require access to some amount of memory. It's going to dictate where those virtual machines can store their data in the physical memory of the hardware. It's also going to coordinate storage, handling the I/O operations of a virtual machine. When you write a file to the hard drive of a VM, where does that data get stored? How does it get structured? And then most importantly, things like CPU scheduling and networking, getting the data to and from the hardware components in a timely manner and getting it where it needs to go, making the most efficient use of the CPU resources on that hardware, and then also getting the networking set up so that the network traffic from one VM goes to the place that it needs to go and comes back from there and doesn't necessarily conflict with what's going on with any of the other VMs. The final layer is then the guest or virtual machine layer itself. It's running in kind of like a sandbox type of environment. It's given virtual hardware that it runs with it. And when you install an operating system on it, it behaves as if you're running that operating system installer directly on hardware. But the physical capabilities of that virtual machine are defined by what you set in the hypervisor. So maybe your computer has, say, 16 gigabytes of RAM in it, physical RAM on there. And maybe your computer has 8 CPU cores. But the virtual machine you need to set up doesn't need to have that much resource. Maybe it's a fairly lightweight thing that you need it to do. So in the hypervisor layer, you can say, well, I only want this virtual machine to have 4 gig of RAM and access to 2 of the CPU cores, because I want to reserve those other resources maybe for other virtual machines or for use directly by the operating system running on the hardware itself. You know, you don't want to have all of the resources monopolized by your virtual machine. And so at that guest layer, when you go to install the operating system, it's only going to see those resources that you give it. It'll think it's running on a computer that only has 4 gigs of RAM and 2 CPU cores and however much virtual hard disk space you decide to allocate to it. And the operating system can be pretty much anything that the hypervisor supports. Now, going back to the whole emulation versus virtualization thing, the limitation is that the operating system you install in a virtual machine has to match what the hardware and hypervisor are capable of. So you can't run operating systems for a different processor architecture on dissimilar hardware. That's emulation and not virtualization. But within the realm of staying within the same processor architecture, say running a Windows virtual machine or a Linux virtual machine on x86 hardware, you're really limited only by what the hypervisor itself can support. And if that guest OS has, got any weird quirks that prevent it from otherwise working in a virtual machine. In most cases, pretty much any flavor of Linux built for x86 is going to be fine. Pretty much any version of Windows is going to be fine. And people have even managed to get modern versions of Mac OS and some other more esoteric operating systems built for x86 like BOS or Haiku OS running in virtual machines with really not much difficulty. So those are kind of the 3 layers. Now, the scale of virtualization can really vary, and this is where things start to get quite interesting. You can have a one-off VM. It can be very small scale. Like we said, where if you're running something like VirtualBox or VMware Player on Windows or Linux laptop, you can just fire up a single virtual machine. And oftentimes that's used by people who need to do like software testing or running programs that your native operating system doesn't support. Say maybe you normally have a Windows computer, Windows is loaded directly on the hardware of, say, your laptop, and you want to run a particular program that's designed for Linux. Well, maybe that won't work directly on Windows, but you could fire up a Linux virtual machine and run the program in that, or vice versa. Maybe you're a Linux diehard and you do almost everything you can in Linux, but you've got this one occasion where you have to run a Windows-only program. You can fire up a Windows virtual machine and just run it in that. Another good use case is if you need to run a program that's too old to work properly on a modern operating system. And this is a good example of what I do with virtualization sometimes at home. One of my favorite computer games is SimCity 2000. And for Windows, it's a 16-bit application. It just doesn't work right on modern, like 64-bit versions of Windows, like Windows 10. So what I'll do is I'll fire up a virtual machine running Windows XP that I've got SimCity 2000 installed in, and it works fine there. It lets me kind of get beyond those limitations. It's also great for other types of retro computing. A lot of people are getting into that, where if there's old games or old programs that they want to run, but they don't necessarily have the space or the money or the time to deal with the old hardware, well, a lot of times you can make all that work just fine in virtualization, provided that, again, that CPU architecture is the same. Getting away from single user type of use, where it's just on one person's computer, their desktop, their laptop, getting into the scope of servers is really where virtualization, I think, got its roots and really started to take off and show a lot of benefit. You can have maybe a single server running several VMs. And this is a scenario that's great for small businesses because it can save them a ton of money on hardware. Think of just any random small business that maybe needs, 5 or 6 different servers in order to operate, right? Maybe they've got like an internal file server and they've got an email server, and then they decide to host their own website. So they've got a web server, and maybe they need a couple of application servers to run, say, their accounting software or their inventory software, or to run specialized machines in their warehouse or something like that, right? So 5 or 6 different servers. Before virtualization, they'd have to go out and buy 5 or 6 physical servers, and servers are not cheap. Like an actual decent server is going to run several $1,000s. So You add all that up and, that company could be spending tens of thousands of dollars for all of that hardware that it has to maintain, that it has to worry about support for, that it has to worry about parts failures on. The costs really kind of add up. With virtualization, a lot of those functions can just get rolled into virtual machines and run on one single server, and one server capable of doing all of those things. Because going back to the whole making the best use of idle time, maybe none of those particular functions requires a lot of CPU or a lot of RAM. Typically file servers, email servers, web servers, application servers, they don't need a whole ton of resources, especially if it's a small business. Well, to buy a single server that can run all of those as virtual machines is going to be a lot less expensive than buying those separate servers, running them on hardware. And of course, it saves on a lot of maintenance and support costs too. The overall reliability is going to go up. There are fewer parts that can fail. It ends up making a lot of sense. But where things start to get really interesting from a technical perspective is when you scale out from just having a single server that runs virtual machines into several or many servers working together in a cluster to run virtual machines. If you remember a video that I posted a while back where I gave you a tour of like these big ass old servers that I decommissioned at my day job, I'll include a link to that up above. I kind of touched on how all of that works, but I wanted to go a bit deeper in to the nuts and bolts in this episode. Basically, you can have multiple servers that all run hypervisor software, and they can work together to run virtual machines. It's a lot more powerful than just having them be standalone. I mean, you could do that too, but by having them be able to communicate with each other unlocks a lot of just kind of mind-blowing features. Now, I should note, when I get into some of these features, there are many different companies that offer virtualization software. Some of them are commercial and some of them are open source. A lot of them have very similar feature sets. But when I talk about a lot of these features, I'm going to be referring to VMware's product lineup, mostly because, one, it's what I have the most experience with and can talk in the most detail about, but two, also because VMware's server product line is very feature rich. They tend to be fairly cutting edge when it comes to what they're capable of doing. So it's a really great example of just the power of virtualization. But keep that in mind that there are other companies that offer very similar features and functionality as well. So clustering servers for virtualization, it unlocks a lot of abilities beyond just that sharing of hardware, gain of efficiency type of standpoint. Obviously, you get centralized management over all of your virtual machines. You get to see the complete collection of virtual machines that you're running on that cluster of servers and be able to manage them with much better efficiency than if they were all kind of one-off. So I need to deal with this virtual machine while it's on this server. I have to go, deal with this server. All the other virtual machines on this other server, I'll have to go connect to that other server. When you've got virtual machines running in a clustered environment, it's what they call a single pane of glass, where you can see it all in a single interface and get a better view as to what's going on and make better management choices as to how to utilize your resources and what performance is looking like as a whole. Do you need to add more hardware to the cluster? Did you buy too much hardware and you can scale it back? All those sorts of things. To get a little bit deeper in to actually running virtual machines, a really cool feature of clustered virtualization is high availability. If you have separate hosts, if you have separate hypervisors and they all run their collection of virtual machines, what happens if one of those hosts were to fail? Let's say it just crashes. Let's say power supplies die, or the CPU has some very bizarre fault, or the motherboard itself fries. All of the virtual machines running on that host are going to crash and burn because the hardware underneath them and the hypervisor layer is no longer there to support them. So it'll be effectively the same as if you had walked up to the server, if it was running on physical hardware, and just pulled like the power cords out, right? They just stop running. With high availability in a clustered environment, all of the servers that run the hypervisor software are communicating with each other. They're constantly exchanging their status, their health state. They're talking to each other. Are you healthy? Are you healthy? What's the status of what's going on? what are you working on? What is this other one working on? They know what's going on collectively as a unit. And so if one of those hosts were to crash and fail with high availability, the rest of the cluster knows what's up. It knows, oh crap, that one hypervisor crashed and burned. But they also know, okay, that hypervisor had these 6 virtual machines running on it, or these 8 virtual machines running on it, or whatever. And the rest of the cluster can negotiate with each other to figure out who's going to pick up the pieces. And within a matter of seconds, they will have all decided, those additional servers running in the cluster will be like, okay, well, server A will pick up these 2 VMs and server B will pick up these other 2 VMs. And they'll basically automatically power the crashed virtual machines back on, again, within a matter of seconds. And typically within just a few minutes, things are back up and running as if it had never happened. Yeah, that one particular host server, that physical hardware, may be down for the count, but typically you design a cluster of virtualized servers with sufficient resources to handle a particular host failure. And so it can just kind of pick up the slack. And, with the additional capacity that the remaining hosts have, the remaining servers have, they can pick up all those VMs and automatically reboot them, and you're up and running again. That's really useful, especially in the middle of the night. If you work in IT, you're probably used to occasionally getting paged because something would break in the middle of the night, and maybe an office in another region that was open at the time really needed access to that. It takes that scope of failure from potentially hours of, geez, the server crashed, we need to get somebody involved who can fix it. They have to physically get there and fix it or check on it and get it up and running. It can take that scope from hours down to just a couple of minutes where the problem basically fixes itself. So that's high availability. Another cool add-on to high availability is predictive failure analysis. A lot of newer hypervisors have better ability into seeing what's actually going on with the hardware on the server itself. And so it can keep track of things that may be going on with the hardware, like if one power supply out of a redundant pair on a server were to fail. Just one, the server is still up and running, but it's only got that one remaining power supply. Or maybe there's a memory fault. Not enough to crash the hypervisor, but enough to indicate, maybe that one stick of RAM is starting to go bad. Something along those lines. With this new predictive failure type of monitoring, that can also get thrown in as a factor when it comes to this cluster communication, where they can not only tell, are all of the hypervisor servers up and running, but are all those hypervisor servers healthy? And so you can end up in a scenario where maybe that one power supply fails, or maybe that one stick of RAM starts to throw a fault. The cluster can decide, you know what? Let's proactively move those virtual machines off of that affected host server and onto other healthier servers in the cluster. It can do that automatically, proactively for you without you even having to really think about it. How does it do that movement though? Well, that gets us into another really, really cool feature. VMware calls it Vmotion, and it's the idea of live migrating virtual machines across hardware. This is really only something that you can do in a virtualized environment. It basically comes in 2 forms. Both of them are pretty wild when you finally wrap your head around it. The first one is called Compute Vmotion, or Compute Resource Movement, where you're moving a guest or VM from one physical host to another. Now, without a clustered setup or without this Vmotion technology, to do that, you would shut that virtual machine down. You would then make sure the files that comprise that virtual machine are available on the other physical server, and then you'd power it up on the other server. So if you end up in a scenario where maybe one physical server needs to have some maintenance done, you need to replace that potentially bad stick of RAM, you could be looking at downtime for the virtual machines running on that particular piece of hardware. A lot of times you can get away with having downtime on servers like that, but you have to coordinate it. Maybe it's something that you can only do in the middle of the night. And I don't know about you, but I don't like waking up at 2 a.m. and hauling my ass into work to either fix something or do maintenance. I would much rather be asleep. So what Vmotion, Compute Vmotion lets you do is live move that VM from one physical server to another without affecting the virtual machine itself. It stays up and running, and in fact, the virtual machine, from the operating system perspective, doesn't even know what's going on. It's happening completely transparently to it, all underneath the scenes here. So how that works is you need to have a cluster of virtual machine servers that are set up with shared storage. Typically, this is going to be something like a SAN, a storage area network, effectively a dedicated server or physical appliance that has all of your hard drives, SSDs, whatever in it, and it connects to all of your virtual servers, your virtual machine servers, the hosts, through a storage protocol like Fiber Channel or iSCSI or NFS. Basically, some sort of way where all of your physical virtual machine servers can communicate to that storage device and have access to the same data. They can all see the same files. If you've got a virtual machine running on physical server A and it's got all of its files sitting on that shared storage, physical server B and physical server C can also see and access those same files. It's called multi-access. And that is really the key to making Vmotion work like this. But when you have that, and in most cases, people who set up clustered virtual environments will have shared storage like that. So it kind of comes along for the ride. What'll happen is when you execute a migration, the hypervisor will start to copy the contents of RAM from the host server to the destination server. It'll do so over a high-speed network behind the scenes, and if you've never seen high-speed networking get saturated, this is an excellent way to do it. Then it starts to keep those copies in sync. Once the same contents of RAM for that virtual machine exist in both server A and B, server A will then hand off control of that virtual machine to server B. Server B will then immediately pick it up and start processing that virtual machine as if it was running originally on that hardware. It'll start executing all the same CPU requests. It'll then handle all of the data I/O to that storage layer because it's got that shared storage access. It'll set up all the networking so that the virtual machine will have the same network access that it did on server A. And because server B has the exact same contents of RAM that server A did for that virtual machine, the virtual machine doesn't know that anything is different. That handoff happens in just fractions of a second. It's so quick and so seamless. You could be sitting there in that virtual machine itself, running commands, working on it, and someone behind the scenes could be live migrating that on you. You just won't know. It's that seamless. The other type of Vmotion is storage Vmotion, and it's kind of like the opposite of compute Vmotion. It's where you have two storage platforms and you need to move the contents of a virtual machine from one to another. Maybe with that whole SAM thing, your company bought a new one, or you have an additional one that has more capacity on it. And for capacity planning reasons or whatever, you just need to move one or more virtual machines from one storage platform to another. It does the same thing. Because all of the hypervisor level, that hardware has access to all those same shared storage resources, it can kick off a copy of all the files that make up a virtual machine from storage A to storage B. When that basic copy is done, because the virtual machine is still up and running, it then also starts to keep track of all the changes that happen and replicate those across. So as the virtual machines themselves read and especially write files down to their hard drive, which turns into changed data at that storage layer, it's able to replicate those changes over. So effectively, you have the exact same contents of that virtual machine's hard drive in both places. And then when they're both in sync, it just does a simple handoff from one to the other. The virtual machine doesn't know the difference. This is another thing that I've done when my organization bought a new SAN a few years ago. I was able to seamlessly move all the virtual machines from the old one to the new one. So the old one could get decommissioned because it was just really old and cranky and slow performing. No one knew the difference. I was able to do it all during the middle of the day, during the week, sitting at my desk. It was a beautiful thing. Now, that virtual machine migration technology kind of comes into play with some other things. One that's really cool is called fault tolerance. This one's actually kind of bananas when you think about it. It's like combining HA and Vmotion, but at a specific virtual machine like guest level. It's a more esoteric thing. Not very many places use it, and there are really only certain scenarios where you want to use it, but it's for those kinds of workloads and scenarios where maybe you've got a specific virtual machine that has to be up and running all the time. It's a very, very important virtual machine, but there's only one of it. And you can't build more. You can't make the virtual machine itself load balancing or redundant. You can't just build two of them and let the two deal with the workload between each other. It's not like, with a web server or whatever, you could have two web servers, put a load balancer on them, and they can kind of share that workload. Let's say you've got a scenario where maybe you work in manufacturing and you've got some very specific machines that do specific work, and they only can talk to one server, and that server is ancient, and it has software that maybe isn't supported by the vendor anymore, and it would be way too expensive to replace with something new. Maybe it's running on an old operating system even, right? So you've got kind of this perfect storm of, this is the one very special server that just cannot crash and burn because it'll cost the company a lot of money. Yeah, the HA and the predictive fault analysis and all that kind of stuff can definitely help you in a scenario where you've got like one kind of golden child VM that just has to be running all the time. But you can go a step further to really ensure that that VM stays up and running regardless of what happens to the hardware it runs on. And that's what fault tolerance, or FT, comes into play. It's basically where you have two copies of that same VM running in parallel on different physical servers. You have a primary copy, and then you have kind of your backup or failover copy. It takes advantage of that live migration technology to continually replicate the contents of RAM between the two, and then also keep track of what's going on with regard to CPU and health state of the two different physical servers, that sort of thing. And so if the physical server that the primary copy of that VM is running on were to just suddenly fail, again, like somebody accidentally pulls both power cords out of the power supply, that sort of thing, it just poof out of existence, that second copy is more or less doing the exact same work as that primary copy of that virtual machine, and it just takes over. The cluster knows, hey, that primary copy is no longer available. It's crashed and burned. You don't need to go through the normal HA behavior of bringing up that virtual machine on a different server. It's already running. Just make it active. And again, that's something that can take a fraction of a second to take effect. And so it can really save your day. Yeah, there may be some other fallout, like if that, original like physical hardware server were to fail. Yeah, there may be outages of other servers as they get brought back online, but that one really important one, it's still up and running, ready to go. Now, why don't people do this for all of their virtual machines? Generally, it's because it's very resource intensive. The hypervisor has to do a lot of work to keep that replication up and running, and so there are limitations as to just how many VMs a hypervisor can do that for. And then also it's kind of going against that whole, like, make the most efficient use of resources, because you're running two copies of the same VM. Can you really afford to do that for all of your virtual machines? And if you could, there are better ways, more efficient ways to come up with that kind of reliability where you load balance it at kind of the application layer. So fault tolerance, it's this really cool combining of different technologies, but it's definitely a bit more esoteric. One that doesn't really help kind of the smaller or medium-sized businesses when it comes to virtualization, but has a huge effect on large companies and cloud providers, is the concept of dynamic power management. So we talked about how you can have virtual machines and physical machines that are kind of bursty in their performance, where sometimes during the day, they're not using very much CPU at all, maybe like in the middle of the night. And then during the day, they're using more, right? Well, when all servers were running on physical hardware before the era of virtualization, regardless of what the workload was at like an application or OS level, all of that hardware had to be powered on and running all of the time, unless you wanted to like physically turn it on and off every morning and every evening, which most people didn't want to do. So we moved into the virtualized era, And we moved all of those physical workloads into being virtual workloads. We turned them into virtual machines. But those physical servers, the hypervisors, generally were still all left on all the time. And when you design a virtual environment like that, you kind of take worst case scenario into account. What happens at peak load? Like when everybody is in the office, everyone is working, it's like 2 p.m, peak efficiency, most systems are up and running and they're seeing the largest amount of load. What do you need to build in terms of the physical resources for an environment like that? So you design for worst case scenario so that all of those requirements can be accommodated. So all those virtual machines can have all the CPU performance and all the RAM that they need. Well, what about the middle of the night when nobody's in the office? All those virtual machines are sitting there idle. And so that means all of the requirements on the physical, virtualization layer are idle, right? The hypervisor level, that host hardware itself, it's all kind of sitting there bored. Or maybe first thing in the morning as people are starting to trickle into the office, it's starting to kind of ramp up, but it's still not all that busy. That in some ways is wasted resources itself. So dynamic power management really extends that resource optimization to the host level as well, where it will actively move virtual machines into a fewer number of hosts when requirements are lighter, when the load is lighter. So you've got, say, normally during the day, you've got all your virtual machines spread across, let's just say 6 physical servers, right? Maybe in the middle of the night, because load levels are low, dynamic power management can move, live migrate, again, with that Vmotion type of technology, all of those guest VMs onto just 3 physical hosts. And there's still plenty of resources to spare there. Well, so now you've got 3 physical hosts that literally have nothing to do. There's no virtual machines even running on them. Well, with dynamic power management, it'll actually power those servers off. It'll actually turn that hardware off to have a real effect, not only on power consumption, but also cooling. So now the air conditioner in that server room or data center doesn't have to work as hard. It can save energy as well. And then in the morning, or when workloads start to ramp back up, it'll automatically bring those hardware resources back online. It'll power them on or bring them out of a sleep state and live migrate those virtual machines back over to them. And so you can end up with this scenario where you're only using as much physical resources as the virtual resources really require. And this is beneficial for large businesses that have a lot of virtual machines where the cost benefit of setting all this up is tangible, where there's a noticeable effect on, say, their utility bill by powering off some of that hardware overnight. For a lot of small businesses, it doesn't really make sense just because the net change in cost is so small. But where it has a huge benefit, the places that gain the most from that are cloud providers, because they're not dealing with hundreds of virtual machines or even thousands of virtual machines. They're dealing with hundreds of thousands or millions of virtual machines, all of which have customers that have very different levels of workload. So the way we've moved is, and this is where it gets into the whole powering the internet thing, the vast majority of servers on the internet really are running as virtual machines. And the companies that run those virtual machines charge the other companies that run the services. Think of the services like Twitter or Netflix or Hulu or whatever. Those companies that provide a service, a lot of them don't even own the servers that they run on. They simply rent virtual machines from a provider, someplace like Microsoft or Google or Amazon AWS. There's plenty more providers like that, but those are kind of the 3 biggest ones. Instead of renting servers in terms of just the technical specifications, hey, I need a virtual machine that has this much CPU and this much RAM and this much hard drive, and then that provider saying, okay, well, it's going to cost you X amount of money for a year or for a month or whatever, they can actually charge by the minute. So you get to a point where if you're a really big service, and Netflix is an excellent example of this, because Netflix largely runs on AWS, Amazon AWS. You look at the load that Netflix has on its systems throughout the course of a day. There are times of the day when lots of people are watching video, and other times of day when not so many people are watching video. Well, obviously, Netflix has to design with that worst case scenario in mind in the evenings when everyone is sat down after getting home from work, eating dinner, and they want to watch a movie. But they don't also want to pay to run that many virtual machines, to pay for that much resource capacity, like in the morning or in the middle of the night when not very many people are actually watching video. So through a combination of that, like resource-based scheduling where they're paying like by the minute or by the hour, and then also dynamic power management, you can have scenarios where the entire clusters of virtual machines can work with the clusters of physical machines to automatically turn themselves on and off based on load. So maybe in the middle of the night, 20%, I'm just making up a number, but maybe in the middle of the night, 20% of Netflix's virtual machines are actually powered on and running in AWS. Well, Netflix is then only paying for that much resources. But then as you get into the evening and it scales up, and maybe it goes up to 80% of what Netflix has, resources available. Well, it can automatically turn those virtual machines on as that load starts to ramp up. And so it's cost efficiency for services like Netflix, in addition to also having to get out of the business of just having to manage all of that hardware. It turns it into a monthly recurring cost for them. It's kind of ironic how interesting it is where, we've seen on the internet, a lot of these services that we pay for are subscription based. It's less you buy a thing and then you physically, own it. You have a copy of it. They send it to you or you download it, and more a subscription based access. As interesting as it is where we as consumers have been going into subscription based access for our needs, the companies that provide those subscriptions are effectively on subscriptions themselves with the companies that they get their resources from. It's just really interesting. So anyway, that's virtualization. It's still kind of a high level overview, even though I went into a lot of the nuts and bolts of it. It's an ever expanding technology and it's ever improving. We've seen, I think, the bulk of the major innovation with it, where things like that live migration and the dynamic power management, but there are still many more places that virtualization can go. It's not something that most people see. I mean, some of you, I'm sure, because I have a fairly nerdy audience like myself, you've probably at least used or heard virtualization to some extent, but the general public has no idea what this is. And it's just this incredible technology that has, I think, made the largest, if not one of the largest impacts in computing in the last 20 years, yet it's completely transparent to almost all of us. Anyway, I am, of course, curious as to your thoughts. Do you have experience with virtualization? Is there a particular aspect to that technology that you are most impressed by? Or have you never heard of this thing before and it's totally opened up your mind as to just how much more complicated computers and networking actually are compared to the way you perceive them to be before? I'm just curious. Let me know what your thoughts are down in the comments below. Also, if you're interested in audio-only versions of these podcasts, I have them available for Patreon supporters at all contribution levels. It's just a plain MP3 download. You can do with it what you want, put it on your phone or play it in the car, whatever. Plus, there's private RSS feed support that you'll get access to. Throw it into the podcast player of your choice. These episodes usually go live a few days before they show up on YouTube, and it's a great way to help support the channel, so I hope you consider it. Anyway, if you like this one, I would appreciate a thumbs up. Be sure to subscribe if you haven't already. You can follow me on Twitter and Instagram at thisdoesnotcomp. And as always, thanks for watching.